Okay, let's do Unit 6 Progress Check Free Response Question Part A. And it is this, and the question begins here. They gave us a table of values, and they give us R, which is the units are gallons per hour. The rate at which oil leaks from a drum is modeled by the twice differentiable function R. R of T is measured in gallons per hour. Notice again, this is a rate that they're giving us, and T is measured in hours from 0 to 2. Values of R of T are given in the table. For selected values of T, use the data in the table to find an approximation for R prime of 3/4. Okay, we're going to find the derivative of that. We're going to show some computations and indicate our units of measure. We're finding the derivative of a rate, which really means we're finding the rate of change of the rate. And we're going to use enough data in the table to find out what happens at 3/4. Well, 3/4 time of 3/4 happens between a half and 1. So we're basically going to find the slope in between these 2 points right here. So let's just jump in with that. I think the best thing for us to do is find R of 1 minus R of 1/2, and then do 1 minus 1/2. Again, this is going to be the slope around a time value of 3/4, and so the denominator is 1/2. R of 1, going to the table, R of 1 is 7, R of 1/2 is 12, so 7 minus 12, and so -5 over 1/2, and that's going to give me -10. Now we're not done, because they did say indicate the units of measure. They did show the work, which we've done. But -10 what? Well, it's a rate of change of a rate of change. So this is gallons per hour, and if that changes, that'd be gallons per hour per hour. Excuse me. So this would be gallons per hour per hour. You could put it like that if you like. Okay, that was part A. Let's jump to part B. And then use a trapezoidal sum with 4 subintervals indicated by the data in the table. Okay, let's just stop and think about that for a second. Trapezoid number 1 is there. Trapezoid number 2 is there. Trapezoid number 3 is there. Trapezoid number 4 is there. Okay, indicated by the table. We're going to do that to approximate this. Now, it is an approximation because we don't have the equation for R of T, but we will just approximate it using the trapezoidal sum, indicate units of measure. Okay, well, let's do it. Actually, here's where my mind just went. Units of measure, the integral of a rate gives me a quantity. So the integral of gallons per hour just takes away the hours. It basically multiplies by hours, and so the final answer will be something gallons. So let's find out what it is. Trapezoids, I have this formula right here, 1/2. I'm going to be going back and forth a lot between here and the table. But 1/2 times the height, and by the height, basically it's the width between 0 and 1/2, which would be 1/2. And then base 1 plus base 2, so 16 plus 12. 16 plus 12, and feel free to go ahead and simplify that. I'm not. Then our next trapezoid is 1/2 times 1/2. This 1/2 is part of the trapezoid formula. This 1/2 is the distance from 1/2 to 1, and then 12 to 7. 12 to 7, and then the next one is also 1/2 times 1/2, and it is 7 to 3. I'm looking at the table. You can't see it, but it's there. And then the next one is 1/2 times 1/2, from 3 to 0, and we are showing some work. So let's keep going with this. By the way, there's another way of doing this. I hope you notice that each of these 4 trapezoids that we have, 1, 2, 3, 4, have a 1/2 times a 1/2. So it's really like 1/4. And then I'm going to just simplify things a little bit. You can do them individually. I'm not. I just personally find this to be a little bit easier. I have, if I factored out a 1/2 out of all of these, I'd have 16. I would have 2 12s. I would have 2 7s. I would have 2 3s, and I'd have a 0, so we're not even going to write that. And now we can go even further with this and begin to take 1/4 of everything. So add these together if you want to. I think I will. So we'll do 1/4 times 16. This is calculator inactive, by the way, so that'd be 40, 54, 57. So 57, something's wrong. Something feels very wrong about that. Hold up. Something feels very wrong. I just noticed what I did wrong, and I hope you noticed what I did wrong too. That's not a 3. I have 2 3s. I only have 1 0, so this is a 6. There we go. All right, that changes everything. Ooh, that was close. Be careful. That was advice to myself. Be careful. This is going to be 15, and they did say indicate units of measure. This is an integral, so it's going to be gallons. All right, part C. Use the data in the table to evaluate the integral from 0 to 1 of r prime of t dt. Now, if you're looking at that saying, well, they didn't give us r prime, they don't need to. Just let's start writing. You'll figure it out. The integral from 0 to 1 r prime of t dt. They did not say, actually, to give the units of this, which, in case you care, would be gallons per hour. This will be the integral of the rate, integral of the derivative of the rate, which would give us the rate, which would be gallons per hour, but that's beside the point. Antiderivative of r prime would be r, and we're going to do that from 0 to 1. This is the fundamental theorem of calculus right here. So r of 1 minus r of 0, and r of 1 is 7, r of 0 is 16, looking at the table to figure that out, and I have negative 9, and it is just simply negative 9. They did not ask for units of measure. We have done part C. Okay, now we get to part D, which has some notation that can be very foreign. This is one of the more obscure topics in calculus, and I'm going to write down what they told me, and then we'll go from there. They said the sum, and this is the symbol for sum, it adds together the following expression all the way from 1 to n. So I'd plug in a 1, plug in a 2, plug in a 3, plug in a 4, add all that all the way up to n of r of 1/2 plus k over n times 1 over n. Okay, they gave me that, and don't panic if it looks ridiculous. It is a right Riemann sum, and that basically is a fancy way of saying that if I wanted to approximate the area of this function on some interval, and we'll talk about what that interval is in a second, then I could do it this way, and we just have a whole bunch of rectangles. So let's kind of back up and do it this way. We're adding rectangles because it's a Riemann sum, and this is the width of a rectangle, and this is the height. And how do you know? Well, the height of any rectangle in this context is going to be the value of the function. So the function is r of 1/2 plus k over n. Don't worry about what k and n are yet. We'll deal with that in a second. But the width is 1 over n. Okay. So this is what we're dealing with. And actually knowing where this is going, I'm going to just kind of go ahead and kind of go in a certain direction with this so you can see where this is going. This will all make sense in just a moment, I believe. And hold on, give me just a second. Just a second. What I'm going to do, pulling up something on my computer. Shouldn't do that while I'm filming a video. What I'm really going to do is write this as an integral. So it's going to look kind of like that, okay? Actually, to be more accurate, it's going to look more like that. So that's where this is going. So in a minute, this is going to turn into this, but we're just going to have to figure out what everything is and what it all represents. So here goes. I am going to figure out what the width actually represents. Hopefully back in the day you recall that on an interval that goes from B to A, so if I go from A to B, sorry, if I go from A to B on some interval and I have n rectangles, then the width of a rectangle is equal to b minus a over n. Hopefully that looks familiar. Well, the width of my rectangle is 1 over n. So if I have b minus a over n equals 1 over n, then b minus a equals 1. So here's what I'm really saying, that b minus a, the width of the entire interval is 1, and that's very good to know. That is incredibly good to know. That's going to come in very handy here in just a second. So the change in the change in t, we could call it delta t, and I'm going to write that down here just a little bit. My delta t is equal to 1 over n, and that is going to be one of the things actually that they are looking for. And if that didn't go through your mind, don't panic. They also need to know, well, first of all, we know the width of the interval is 1. Another thing that we need to know is where does this interval begin and where does it end? And the answer key says that the interval can be taken to be from 1/2 to 3/2. Let me clarify that a little bit for you here. By the way, this is about to be my final answer. Just saying, something dt. Change in t is 1/n, and if I started at 1, if I plugged in a 1 for k, I'd have 1/2 plus 1/n. Well, n is approaching infinity because they said so. So I basically have 1/2 plus 1/huge, which is basically a half. So this x value, t value rather, that I would plug into r would start at a half. And if I count all the way up to infinity, I'd have 1/2 plus infinity over infinity. Now that's technically an indeterminate form, but it is something in this context. It's something over itself. So I'd have 1/2 plus 1, which would give me 3/2. And so basically, my function is what I'm evaluating. And there's the width. Delta t is my width. I can call it delta t, you can call it dt in this context. And it starts at 1/2 and it goes to 3/2.